All right, so it says find the z-score that has 11.9% of the distribution's area to the right. So this area, we're not talking about z-score on the x-axis, we're talking about an area, 0.119. This area is 0.119. So if I just look up the 0.119, that'll give me a z-score over here on the left side. So I could actually, this area up to the left, 0.119. If I look up that score, if I go to the table and look for 0.119, it'll give me a negative z-score. But this should be a positive z-score. And in fact, it's the exact opposite of whatever you find here. So I mean, there's multiple ways to do it. I'm gonna write using notation. Okay, find the area, find the z-score when the area is 0.119. So on the calculator, the notation would be inverse norm. Inverse norm 0.881. You could write like this. If you're asked for an area, the area is going to be 0.881. And how did I get that? I did 1 minus 0.119. The area to the left is 88%. The area to the right is 11.9%. The mean, 0, standard deviation is 1. We don't have a mean or standard deviation in this case. If I did, again, inverse norm 0.119, that'll give me a negative z-score, negative 1.18. So you might come up with a negative z-score, negative 1.18. But this z-score is positive 1. This is negative 1.18. This is positive 1.18. Looking in the table, I'm going to go look for 0.119 in the table. So when I go to my table, I'm going to be in the table. I'm going to look for a z-score of 0.119 in the standard normal table. Why am I using the fold out? I don't know. Got to fold out. 0.1190. I see it. It says negative 1.18. Does it make sense? So if I actually want the positive, I'm going to look at A17 and I'm going to look up 0.881 and I'll see 1.18. So that's the answer. Z equals 1.18. All right. So areas to the right. This is really important because later on when we do this called significance testing, we're going to find right tail areas, z-scores for right tail areas, and we'll have to find z-scores for left tail areas. So it's in a significance test. We're going to have to continue doing this thing. So you're going to see it continuously throughout probably the rest of the course. Okay. In any others? So that was from 5.3. 5.3 is where we did the inverse of finding, given area, find the z-score. Anything else? Yes. Oh, like what it's all about? Yeah. Okay. 5.4 review. Okay. So let's look at 5.4 real fast. So the idea is when you get a z-score, that's the formula that we typically use. Those are population parameters. Mu and sigma are population values. So if something's happening in the population, the average GPA for Hancock students, 2.8, that's population, standard deviation 0.5. But if I ask 30 students and I get their average GPA, I want to know if my statistics students have a higher GPA than the rest of the population of the school. I ask my 30 students in statistics, hey, what's your GPA? And I get everyone's GPA and I find the average GPA. I don't want to compare an individual one score. I want to be like, hey, Tito, what's your GPA? You know, and compare his score to everybody. That's what this does. I want to take the average of the entire class, and I want to say, I think my students' GPAs are higher than the population of the entire school. So in order to do that, I would go like this. The average of all my students minus the mean divided by that standard deviation. So now I'm going to take the average of Hancock students in statistics, 3.0, minus the average of all students in the school, 2.8, and compare them. It's a comparison tool. Well, I got to divide by the standard deviation of the sample. So this is called sampling standard deviation for the sample mean. So n is 30, so I plug in 30 in there. This is 0.5. So I can do all that now. Okay, what does that mean? I'm going to use this curve right up here. I'm going to get rid of all this. So if the population distribution is, if the mean is 2.8, this is in terms of GPA. So I could draw the curve on there. This is what's happening with everybody at Hancock College. Okay, all students. Add 0.5, add 0.5, subtract 0.5, subtract 0.5. So I could say, using the empirical rule, about 95% of students at Hancock will have a GPA between 1.8 and 3.8. Right? There might be a few that are below, there might be a few that are above, but not that many. Okay? It's going to be a small. So that's using the population. That's this. But I want to take a sample of 30. So in a sample of 30, compare my students to everybody in the population. And that's what we're doing. Where's 3.0 at? That's over here. That's above average. But how far above average is that? I can't use this distribution anymore because I'm sampling 30 students. Well, the population mean, we call it mu x bar, is probably going to be about 2.8. Okay, so that's what this would be. We say the population mean is going to be equal to the sampling distribution mean. And deviation is going to be 0.5 over the square root of 30. So this distribution is going to be modified. I'm going to do that math right here. 0.5 divide square root 30, 0.091. I hope this is a different example that I did the other day. I don't remember. That number sounds familiar though. I think I've seen it before. It's the same exact thing. Okay. Sorry about that. 0.091. That's the standard deviation. So that's like 1 grade point. 0.09 is pretty close to 1/10 of a grade point average. That's the new standard deviation. So if I do my new standard deviation, it's going to be much more narrow. 2.8 in the middle. 2.89 and 2.71. At 0.09 again. Am I able to do this? 2.98. Okay, so 3.0 is now like 2 standard deviations above average. So I'm saying if the average is 3.0, is that unusual? So anything out here is considered unusual. Anything that happens less than, that's about 5%. In between the 2 standard deviations is 95% of data. Outside here is about 5% of the data. So we consider that unusual. So where's 3.0 compared to 2.8? Well, anything out here is considered unusual as well. So 3.0 is in the unusual zone. So 3.0, having a GPA average of 30 students having a GPA of 3.0 is unlikely. It's unusual. It's like a reverse proof. It's like saying that that would be in fact true that the students in this class have higher GPA than on average than the rest of the student body. So 3.0 is high above 2.8. If 3.0 was close to 2.8, like in this range, I would say there's not much of a difference between those two things. One of the main things about this is kind of like if you're in algebra. If you're in algebra, you learn the slope of a line. Oh, here's a line, a straight line. We're going to study the slope of the line. And then we're going to write an equation for that line. That comes later. Okay, so you learn slope, then you learn the equation. This is similar in statistics. We're learning about this new formula, but later we're actually going to use it to answer questions like this. Is that unusual? Is this likely or unlikely to happen? Okay. So that's something that's going to come down the road. So this is like a preview of those things that we're going to do in chapter 7. And so it's going to come, it'll come back later. I don't want to say come back to haunt us, but it's going to be very useful for understanding normal distribution curve and applying means to populations. Again, 5.4, I'm not really, I skipped 5.5 because that it gets even crazier. 5.5, it's pretty gnarly, but 5.4, not too bad. We went over example 5. Example 4 was a good one as well. But example 4 asks you to find the probability of getting a, it's on page 256 and 257. 5.4, I don't like the problem because it says you select 50 drivers and look at their travel time to work. What's the probability of spending between 24.7 and 25.5 minutes to get to work? To me, that's just a silly question. It's like, why would you want to know what percent of people are taking that much time to get to work? Doesn't make any sense. A better question would be like, find the probability it takes less than 25 minutes to get to work for this group of 50 people. Does that make sense? So the in-between thing is like, that's less than a minute, 24.7 and 25.5 minutes. That's just less than a minute. We're going to find this range. It doesn't make sense to me to ask that question. It's not really applicable. A better question would be say, on the probability it takes less than 25 minutes to get to work, or less than, that's over here. On the probability it takes more than 30 minutes to get to work. 30 minutes, that's over here, because 25 is in the middle. Okay. But example 5 is a good one to go back and read through and try to grab onto. But again, we use the mean and this new standard deviation value when we're doing our calculations. Okay, so if they ever give you a sample size, they say we sampled 50 people, then we know that we have to do this. If they don't give us sample size, then we know we can do this. So there's 2 different z-score calculations that we can do. I hope I helped. I did the exact same. Well, it wasn't identical, but I used the same values to reiterate what's going on there. Anything else? 5.4. But again, we're going to find a z-score. We're going to find a z-score. Oh, 3.0 minus 2.8. And then we look up that z-score. 3.0 minus 2.8 over 0.091. And you get a number a little bit bigger than 2. I didn't finish that calculation. 0.2 divided by 2.19. That's a z-score that's a z-score of 2.19. There's a z-score of 0, z-score of 1, z-score of 2. Now z-score is 2.19. Find the area over there. Find the area to the right of 3.0 is what we would have to do. And that will tell you how likely this is, the chances of that happening. And you end up with like 0.02%. Or I'm sorry, 0.02, which is 2%. 0.02 is 2%. So that's the area to the right of 3.0. Okay. Cool. I guess we're ready to move forward. Let's do chapter 6, new stuff. Okay, I already gave my disclaimer for chapter 6. chapter 6 has this new formula that the book shares. But I'm going to modify it a little bit, and I'll explain how it works. We're ready, 6.1. And the title of chapter 6, section 1 is confidence intervals for the mean. For population mean. So there's another way to look at statistics. Usually you want to find the average value, okay, and that's what most people are focused on. What do you think the average temperature in Santa Maria is in July? Like last night, I could almost guarantee that it would have been foggy last night, because every year on the 4th of July in Santa Maria, I've lived here for about 43 years and been foggy on the 4th of July pretty much every year. So I was pretty sure it was gonna be foggy last night, right? What's the average temperature in July in Santa Maria? Well, probably about 72 degrees. Okay. That's a mean. That's a mean value. And we get the weather report. Anybody have a weather app? Anybody follow the weather? Oh wait, you guys aren't over 60 years old. You know, anyone over 60 years old, that's what they like to talk about, right? Like, oh, the weather and the temperature and all this stuff. And I just pull out my weather app. I don't need it. No, it says right here. They're like, oh, those things are wrong. Well, it's not going to be 100% accurate. Oh, it said it was supposed to be 70 today. It was only 68. You know, you got to have something to complain about. But that's a mean, right? It's a value that we're trying to target. Well, wouldn't it be easier if you said, I think the temperature is going to be in between these two values? Okay, so if I say what the exact value is, that's called a point estimate. I'm trying to say exactly what number I'm looking for. Okay, and weather people, they use statistics to come up with weather forecasts. Okay, so part of it is coming up with in between what two values is going to be, and then they pick a value. Well, I think the temperature is going to be between 65 and 75 degrees tomorrow, right here, as we walk into the door. Okay, the high temperature. So then I can narrow it down. If I think it's going to be between 65 and 75, then we'll call it 70 degrees. Okay, so I'm going to come up with an interval. It's going to be in between two numbers. And here's how I just wrote this. With an interval, we're saying in between two numbers. I'm going to use some notation here, because I'm going to use this when we come up with the formula. 65 plus or minus 5 degrees. So that's a little calculation right there. That means add 5 and subtract 5. 65 plus 5 is 70. 65 minus 5 is 60. I gave the wrong number. It should have been 70 degrees. That's the one that I said. I might as well stick with it. I think I said 70, right? Yeah. So it's going to be in between these two numbers. I'm pretty sure. I've lived here for a long time. I've been in many Julys. And the hottest month here is usually like August. It's the hottest month in this city. So we're not even there yet. There's an interval, and usually we write intervals with parentheses, and we put the two numbers in there, like as a point, like an algebraic points on a grid, right? So this is the lower bound. This is the upper bound. Okay. Some people get confused, and when we get into the formulas and we're doing this hardcore statistics stuff, some people will put the smaller number second and the bigger number first for some reason. I don't know why. It just makes sense. Small number first, bigger number second. This number right here, that 5, is called the margin of error. This number right here, we're going to call that the mean, but not the mean, not the population mean. We're going to call that a sample mean. So how do people forecast the weather? They pretty much know based on the last 5 days what's going to happen tomorrow. Okay, stock market works that way. Based on the last 5 days, what's going to happen tomorrow with the stock market? People predict what's going on with the stock market. People bet on the stock market every day. Hedge funds and mutual funds and all these things. And there's a lot of millionaires and billionaires out there that do that, right? They're just betting on the stock market is going to gain or is going to fall. So using statistics, is it a growth or a decline? So they can take sample mean based on what's been going on, add or subtract the margin of error, and that'll give me an interval. So this margin of error is really important. This margin of error comes from an amount based on a sample size. Okay, so if I have 50 people and I'm trying to come up with the average GPA, I'm not going to say, oh, the average GPA is 2.8. I'm going to say, I'm going to ask 50 people, get an average GPA of those 50 people. Oh, the average of the 50 people is 3.0 plus or minus a margin of error, plus or minus 0.2. Okay, so then I'm going to say, I'm pretty sure that average GPA is in between these two numbers. So this margin of error is what we're going to focus on. The book gives us the margin of error is based on z-score. So I'm just going to give you the formula. This is the sample mean called x bar, plus or minus. The margin of error is like this, z star, standard deviation over square root of n. And we've seen that one before. So like I said, if there's 50 people, I'm going to calculate the margin of error. So all this information is going to be given to us, except for that z star thing. That's the news. Well, we know what a z-score is, but that's a different, that's not z, that's z star. So we're going to come up with this number based on a confidence interval. Here we go with curve again. I'm going to stick with this idea of the GPA. So if the average GPA, if I ask 50 people, so we say n is 50, and the mean of those 50 people GPAs is 3.0. Okay, that's pretty good GPA. I asked 50 people. I randomly picked 50 students in the college. I'm trying to come up with the population mean. The sample mean is not going to be equal to the population mean. 5.4, what we did was we took lots of samples and found the mean of the means. Remember calling that the mean of the mean? Standard deviation, population standard deviation is 0.5. Stick with the same values that we just had previously. So now I need to come up with curve. Well, we already did this. I changed the sample size to 50. So my standard deviation is going to be a little bit smaller. So I'm going to come up with a confidence interval. We're going to use this formula right here. So I'm going to show you what it would be with one standard deviation. So 3.0 is in the middle. I got to calculate the standard deviation for the sample mean, this thing, standard deviation over square root of n, which we just did. 0.5 over square root of 50. 0.5 over square root of 30 was 0.091. Let's see what this one is. 0.5 divided by square root 50, 0.071. But I'm not just going to multiply this. This is 0.071. I'm going to multiply it by a z-score. So I want to go 2 deviations to say what would be usual. So standard deviation, one standard deviation is 0.071. So this would be 3.071. This would be 3.14. Subtract 0.07, 2.93, and 2.88. Okay. So I just did 0.07. I just estimated that to be. Okay. So I'm pretty sure that the average GPA of all students in the college, it's gonna be in between these two numbers, because that's most likely event to occur. 95%. Remember the 95%? That was 2 deviations. So it comes out to about 2. But I'm gonna take 2 and multiply by 0.071. That'll give me the margin of error. So let's do it. Let's do the formula. So sample mean was 3.0 plus minus. I'm gonna save the Z star deal in a sec. And I said, let's go 2 deviations. That's what I did here. Okay, so this number is what I want to focus on here for a second. I'm going to come up with that number, which is, I'm going to make a table here. It's called our confidence level, or our C level, and our Z star. So for 95% confidence, we would be 2 deviations. 1, 2. That would give me the 2.88 and 3.14. But we're not gonna, 95% is not exactly 2.0. Okay. And I'll show you where it comes from in a little bit, but the Z star number is not gonna be 2.0. It's a number really close to 2.0. It's actually 1.96. So with 95% confidence, I'm pretty confident. I'm pretty confident that I'm gonna get the GPA of everyone at Hancock. So I'm gonna use a 95% confidence level. The higher your confidence level, the wider your interval will be. If I use 90% confidence, I'm gonna give you 1.645. We were finding that number when we used the table last week. We used the table and I was like, this is a really important number. We're gonna use it a lot. 1.645. That was 90%. And another one that we're going to use a lot is 99%, which is 2.576. And all of these numbers appear in the book. Where's my little table? Page 299. If you want to know what these numbers are, you go to page 299. Again, we're doing all this. This is how you need these numbers if you're going to do it by hand. If you're going to do it on a calculator, you're going to use to chill for a couple minutes until I say, hey, pull out your calculator. We're going to do it on the calculator. So anyhow, the Z star for 95%, which is the most common one, confidence level, 95%, that's 2 deviations. That's considered normal or usual. I'm going to use the 1.96 value right here. So I'm going to substitute this for 1.96. Okay, I'll talk about confidence in a couple minutes. We'll just finish this though. So I'm going to do some calculations here. Multiply by 1.96. I just multiplied those two numbers. This is the sample mean. This is called the margin of error. Okay, said here, margin of error, 0.139. Now I'm going to add and subtract 3.0 and 0.139, 3.139 and 3.0 minus 0.139, 2.86. Let me use the exact number. Yeah, okay. So I'm confident, I'm 95% confident. I'm 95% confident that the population mean GPA is between 2.86 and 3.14. I'm pretty confident in that. Because I took a sample of 50 people. I had a pretty large sample. 50 is good size. 30 is about as low as you want to go. 30 means you got a large enough sample size. Well, let's compare these numbers. Look at, I drew the curve up here already. 3.139, that's like 3.14. There it is right there. 2.86, I was a little bit off on that one. I don't know if I did the math wrong or what. Oh, I did do the math wrong. Because the standard deviation was 0.07, 2.93, take away 0.07, it's 2.86. I just had the wrong number there. So I found the answer. I had it on the board. I already knew what the answer was going to be. So I subtracted 2 deviations. Well, it's not exactly 2, it's 1.96, but I did 2 deviations. Considered normal, okay? So the sample mean is 3.0. This tells us where the population mean is going to be of all students, right? There's 10,000 students at Hancock. Am I going to go ask 10,000 students their GPA? Do you think the registrar's office has that information? They probably do, but it changes every semester, right? So I want to know what the GPA is this semester. It's going to be different than what it was last semester and the semester before that and last year. What's going on right now? So finding that value right now is really important. What's going on with the school? Texting or iPhone usage or what percent of people have an iPhone? That changes all the time. This information, statistics, what's going on right now, the data is collected via survey. They call you, right? Or they call companies and get information, get your data. And everyone says they don't sell your data, but they really do. And why do they want your data? Because they want to know how to make money off you, right? So we get the data, we get the information, we come up with things like this. Okay, I'm going to talk about this confidence level business right here real quick. I think that the temperature tomorrow is going to be between 65 and 75. So I have this confidence level. How confident am I in that interval? I would probably say I'm about 80% confident. There is a possibility we could have a temperature above 75 degrees tomorrow. I haven't checked yet on my weather app. What if I said I think temperature is going to be between 50 and 100 degrees tomorrow? Do you think I'm more confident in that or less? More or less? Okay, I'm pretty sure it's going to be between 50 and 100 degrees tomorrow in this city. Pretty confident in that, right? I'm like, yeah, for sure. It's not going to be over 100 degrees tomorrow. It's not going to be below 50 degrees either. So the more confident I am, the bigger my interval is going to be. So I'm going to have a wider interval. So if I had even more confidence, check this out. If I did 99% confidence interval, my Z star is 2.576. So these numbers would be, this number would be bigger because I'm now, instead of multiplying by 2, I'm going to multiply by 2.5. I'm going to have a wider interval. I'm going to have more confidence. If I had less confidence, I'd have a smaller interval. This interval at the end will be smaller. There could be many different confidence levels. There could be an 88% confidence interval. There could be a 92% confidence interval. A lot of these are in the table. There's a table. Let's go to the back of the book. We're going to investigate a new table. A16 and A17 is bookmarked. Go to A16 and A17. That's my one bookmark page that I got. Then I'm going to go one more. We're on a new table. New table. Next page. This is called table 5. Table 4 is standard normal distribution. We're going to go to table 5. At the top of table 5, it says level C confidence. C level. Okay, at the very top are confidence levels. And this table doesn't have all the confidence levels. We could find them if we really wanted to. There's the 80%, 90%, 95, 98, and 99% confidence intervals. So notice 90, 95, and 99 are on there. These numbers are on there. Where are these values at? These Z critical values. They happen to be at the very bottom of the table. So go to 95%, put your finger on 95%, and just go to the very bottom of the table. And there's the 1.96. Go to 90%, go to the very bottom. 1.645. So they're in this new table. This is called a T table, actually. We'll use it today. The 99%, you see that on there as well. We can also get those numbers from the calculator by doing an inverse norm, like we did in 5.3. Okay, if I do inverse norm, if I want to know for 95%, where the 1.96 come from? Well, if the middle is 95%, if this is 95% right here, that leaves 5% for this one and this one. So what I do is I take 100 and subtract 0.95. That gives me 0.05. That leaves 5% here and there combined. Then I divide by 2. That gives me 0.025 or 2.5%. So I get 0.05 divided by 2. That gives me the 0.025 over here and 0.025 over there. So if I really want to know where this 1.96 comes from, I look up 0.025. It's in the table. It's in the standard normal table. So all these values that are in this table come from the standard normal table. So let's go back to A16. Look for 0.025. It's in there. Negative 1.96. This z-score is not -2. -2 is the empirical rule. Okay, the empirical rule is just like a rule of thumb. It's an estimate. It's an approximation. The actual z-score value here is negative 1.96. The actual z-score value here is positive 1.96. And we add and subtract 1.96 because we want this value here and we want that value there. And that's what the formula does for us. This formula is called a confidence interval formula. Okay, or a Z interval. If I write it right up here, Z interval. Because later we're going to do what's called a T interval. Okay, so it'll modify it slightly. So everything I gave you right here, this formula, it's not in the textbook. If you go look through the book, you're not going to find this formula. The textbook goes something like this. X bar minus E. X bar, oops. X bar plus E. So this is what the book says. If you're following along in the textbook, the book says this. And then the book says, oh, by the way, that E thing is Z star times standard deviation over the square root of n. So they told us this is a new piece of information. So now I'm going to plug that into this formula. Z star okay, so I had to plug it in. It's the same thing. Do you see that it's the same thing? There's the minus and there's the plus. I like this formula for only one reason, because it says the mean, the population mean is going to be in between those two numbers. The population mean is going to be in between these two numbers. Okay, that's what our confidence level states. Well, instead of writing the formula twice or writing these two numbers in here, I just wrote it one time and put a plus minus there. Okay, so it's like a shortcut for this big long formula. There's no, oh, E is this other thing. E stands for margin of error. Okay, so all of this is margin of error. The mean, the sample mean is always in the middle. So again, the book addresses it. So when you encounter that in the textbook, is It begins on page 301. At the top of page 301. X bar minus E is exactly what I wrote right there. And then on page 300, they give you the E value, the margin of error. Then they give you guidelines for constructing a confidence interval. Well, the guidelines are take your values, plug them into the formula, find your Z star based on your confidence level. Voila, you got it. Okay, substitution. In math world, mathematicians call it plug and chug. You plug in numbers and chug out and do all this math until you get to your answer. Like you get into physics, anybody ever take physics? They get 1-page long problems. It's pretty crazy. So anyways, that's the long way. You ready for the calculator way? In calculator way, we could it bypasses having to find the Z star. We skip this whole step. Pretty cool. We're going to a new world, Super Mario World number 3. We press the stat button to get there. But then we go to test, stat, test. And what kind of tests are we going to do? Well, there's the Z test, there's a T test, and there's a 1 sample and 2 sample T test. We're not testing yet. This is not a test. This is called an interval. And what kind of interval is it? It's called a Z interval. See if you can find it on your calculator. Number 7, you say? Number 7 is a Z interval. Does that make sense? I go stat, go to test, go to Z interval. That's exactly, it says exactly what I put right there. Then there's the first question that pops up. It says, do you have data or do you have statistics? Well, if we had data, for example, in this problem, the average GPA is 3.0. If I had all 50 GPAs, that's data, right? I have everyone's GPA. I can plug it into a list, but we don't have that. We have statistics. These are statistics. So I'm going to choose stats, highlight stats. Standard deviation, population standard deviation was 0.5. That was given. Population mean, 3.0. That was given. And sample size, 50. That was given. Sea level. Sea level is going to be your only decimal that you're going to put in here. So sea level was 0.95. And then calculate. 2.8614. 3.1386. Yeah? A little faster. What do you think? Can you use your calculator to calculate confidence intervals? Yes. I like show how to do it by hand and then how to do it on the calculator. So let's do a practice 1. Page 303. Example 5. I'll read it. We're just going to do it on the calculator. We don't have to do it by hand because they did all the work for us. A college admissions director wishes to estimate the average age of all students currently enrolled. In our sample of 20 students, the mean age was found to be 22.9 years. For past studies, standard deviation is 1.5 years. Population is normally distributed. Construct a 90% confidence interval. Construct a 90% confidence interval. So go ahead and go to Z interval on your calculator. See if you can do it. Okay. Did we get that yet? Yeah, Z interval on the calculator. We're in stat test. Go to number 7, Z interval. We don't put 1.645. This was a 90%. We only use that number if we calculate by hand, 1.645. So I did by hand right here. I did not use the book formula. I used my handy dandy formula right here. This margin of error was 0.6. We have 0.6 margin of error, and this is age of students. So the average age of 20 students was 22.9 years old. What's the average age of 10,000 students? The average age, I don't know what it's going to be. It's not 22.9. That's the average of 20 students. The average age, I'm 90% confident, the average age is between 22.3 and 23.5 years old. So it gives us an interval of those two values. Anybody having trouble with calculator? Anybody stuck? Yeah. 0.9. Population standard deviation was 1.5. Sample mean was 22.9. The sea level is 0.9. N is 20. 20 students in a random sample of 20 students. Yeah. So how do we interpret this thing? It says at the bottom there in example 5, with 90% confidence, you can say that the mean age of all students is between 22.3 and 23.5 years old. So we take a sample mean and we're saying the sample mean is cool and everything. I'm not going to ask 10,000 students what their age is, so I'm just going to take a sample. That sample average is not going to tell me what's a population average, but I can say, oh, it's going to be in between those two numbers. I'm pretty confident it's going to be between those two numbers. If I increase the confidence level like a 99%, that would make this interval wider, bigger. Okay. Margin of error. Okay, I didn't address a couple things, but the book, some of the questions will ask you for the sampling error. The sampling error is the difference between the sample mean and population mean. So there's a word called sampling error. How far off is our sample? So if the average age of our sample is 22.9, the average age of the population is 30, we're off by 0.1 years. We just subtract the two numbers and population mean. That's called sampling error. The margin of error was this thing. This thing's called the margin of error right here. All together, margin of error. There's a couple of matching questions. You might need to do all the matching questions, not just one of them, in order to figure out the matching problems in the homework. And do 5 through 33 odd. And when I say 45, and I think it was 45. 35, 47. Thank you. Okay. The first half of the problems, like before, a couple of problems, you're just subtracting two numbers. Okay. So they start off real slow and they develop. By the time you get to problem 33, you're going to have to do this. Okay. So this is at the very end. Problem 47, this one right here. I'm gonna let you guys work for about 30 minutes and then I'll address problem 47. So if you actually get to problem 47, which I doubt will happen in 30 minutes, then just hold off. But now it's break time, whatever you need to do. Now it's work time, 30 minutes, go until 7 o'clock. See if what you can get done. Sound good? All right, cool. All right, any questions about finding the minimum sample size? Minimum sample size, page 304. Call it the N formula. So when the question pops up, find the minimum sample size. Formula we use. And there's no shortcut on the calculator for this, like that formula. Okay. That's a Z interval. Any questions about any of the problems out there? Pretty good. Okay. All right. We're ready for more. That's a punishment. Continue. All right. We're going to take the same idea, the same formula. We're going to find confidence interval and build on it. We're going to build on confidence interval. So we have standard deviation. This is a population value. But sometimes that number is not given. Sometimes we don't know the population standard deviation. Well, in fact, most of the time, we don't know the population standard deviation. We don't know the population mean. How are we going to know the population standard deviation? So again, if I ask 50 students at Hancock, what's your GPA? And I get an average GPA for Hancock students. I know what the average is, but I don't necessarily know what the population standard deviation is. I know what the sample standard deviation is. So when we do this, there's more margin of error. Because standard deviation, when this thing is unknown, we cannot do a Z interval anymore. Again, this is called a Z interval. When standard deviation is known. If we don't know the standard deviation of the population, we have to do a different formula. And it's called a P interval. And it looks almost identical to what we just found. A couple tweaks, a couple modifications. So I replaced the population standard deviation with S. S is sample standard deviation. This is a more common confidence interval to use because we take a sample, all the information we have is based on that sample. I could ask everybody in this room their age. I'll know everyone's age and I'll find the mean of everyone's age. I could also find the sample standard deviation of everyone's age. Do I know the standard deviation for everyone's age in the college? No. I only know my information based on the sample data that I collect. Okay, so it's more realistic to know the S. Those T intervals, standard deviation is unknown. So we have two intervals that essentially do the same thing. So we got this new T star value. This T star is based on your sample size. The T star is based on your sample size. So we're going to spend some time trying to figure out this T star value before we get into an actual problem. All right, so if I say our confidence level is 0.95 and our sample size is 21, what is my Z, which we did before, but now we're going to say, what is my T? In order to get T, we have to use the T table, or we can do inverse T. Not everybody's calculator has inverse T. It's like inverse norm, but inverse T will give us this T critical value. I want to use the T table. So we're gonna, we looked at it already. It's table 5 in the back of the textbook. We're gonna use table 5 now. So I go to A18. So A16 and 17, I have bookmarked. I'm going to A18, the very next page. And it's called a T distribution table. The T distributions have more spread than the normal distributions because there's more margin of error. When you base your information on a sample, you have more margin of error. So I'm gonna look at the table. Down the left side of the table. Down the left side of the table, it says DF. Those numbers down the left side of the table are not N, sample size. Those are called degrees of freedom. So in this problem, degrees of freedom is 1. We subtract 1 from our sample size. That's all. Degrees of freedom is probably the easiest formula that we'll ever see in statistics. Subtract 1. Remember the standard deviation formula? X minus X bar squared divided by N minus 1. I don't know if you remember that. There was an N minus 1. That's degrees of freedom. The mean, you divide by N. Standard deviation, you divide by N minus 1. There's a complicated reason why. Divide by N minus 1, but it just maximizes our margin of error. Okay. So I'm going to look at the table. I want to go to 20 on the table, go down to 20, and I'm going to start going across, and there's 5 different values I could choose from. Well, what's our C level? 0.95, you see it right there? Confidence level will be given. .086. Why do we need to know that? Because we're going to take this value and plug it in to this formula. Instead of using 1.96, we're going to use 2.086. A little bit more than 2. For 95%, if it's a Z, we use 1.96. If it's a T, we use 2.086. So our margin of error has increased slightly. Okay. Because our sample has a small sample size of 20. 20 is a small sample size. This is how we find T. Try another one. Let's say C is 0.9. N is 32. What is your T star? So I just go to the table. I go down to 31. Yeah, 1.696. Cool. Yes.
It says N32 up there. Why would you just go down to 31?
So N is 32 on the left side. Those are all called at the very top. It says DF. Those numbers are not N's. Those are not sample sizes. Those numbers are called degrees of freedom. Degrees of freedom is N minus 1. So we take that 32, we subtract 1, That gives us the degrees of freedom. So on the left side, it. Later on in other tables, they'll give us n. I don't know why they don't do that. They should just give us an n, just be like, okay, if n is 32. Use the number that's just above. That would make things a little easier. Statisticians like to complicate things a little bit. That's using the table. We got to apply this knowledge to something, a problem, a word problem. Because that's what we do. We interpret word problems, try to make sense of them. So we're on 6.2. And we're going to go to example 2, page 312. So we're just going to read through. I'm going to do this a little bit different than what we've been doing. I want you to read the problem. Think about what you would do. Okay. Then read the solution. See where everything is substituted at. Okay, so all the numbers are plugged in. And then we're going to discuss it, and then we'll go to our calculator and do it on the calculator. Okay. So about 5 minutes doing that. Very good with that? Yeah, okay. Again, they have guidelines. They want you to memorize 5 guidelines to constructing a confidence interval. Constructing a confidence interval. Start off with the formula. It's not in the book. Plug in the numbers. 162 is the average temperature of coffee, 162 degrees. I wonder why it burns my mouth. Okay. T star, 2.131. Where'd that come from? Well, again, that's based on the sample size. We got to use the table. There's an inverse T. I'm not going to go into inverse T because some people don't have it on their calculator. Some calculators do not have inverse T. If you go to stat and bars for distribution, there's T interval in there and there's inverse T. We're going to do this on our calculator. That's what it's called. Okay, there's a Z interval. Right underneath the Z interval is T interval. This one was number 7. This one's number 8. T interval. So again, stat, test, number 8, T interval. We have statistics. We don't have data. Some of the problems will give us data. They'll give us the values of everything. The mean is 162. S was 10 and 16. Oh, sea level. We didn't even have to find 2.131 if we use our calculator. This is a 95% confidence interval. Calculate. 156.67. Yep. 167.33. Cool. Was everybody able to get on the calculator? $156.67, 167.3. So it's just like a Z interval. Except now we got to find this T critical value. Okay, that T number. And there's a couple of examples that I'm going to leave up there. So hopefully you didn't look at that, use that to do some of the problems. The problem set's a little shorter on this one because this is a really short section actually in the book. 13 through 33 odd. 13 through 33 odd. Less problems. There are a couple problems where you have data. Okay, so if you're going to do it on your calculator, you choose data, you enter all the data into a list. And when you choose data, it'll say, where's your data at? And you probably just put it in list 1. So it'll, by default, will say list 1 when you press data. So let's look at that real quick. Press stat. Go to test. And we're going to go down to T interval. Press enter. Choose data. And then press enter. List. List 1. That's where you want to put your data. Frequency. Always keep your frequency at 1. Okay, don't change the frequency, FREQ. Sea level. Well, that's based on whatever confidence level they gave us. So we don't even need to have the mean or the sample standard deviation because the calculator computes that using the data that's in our list. Okay, if you try to do a calculation right now, you might get an error if you don't have any data in list 1. I got a confidence interval for my data in list 1. It worked. That's it for today. Only 8 o'clock, early day. So try to stick around, maybe do a few problems. You don't have to if you don't want to. What, you rather work at home, you can, dealing with fireworks going off. My neighbors are shooting them still. Today, and saved them for some reason. Oh, I know why they saved them, because police came and said, hey, go away.
Yes.